So this is my demo for the Avian Acoustic birdsong recognition application using machine learning um, as my uh, main model to pursue and build for this classification task. So I'm going to fast forward here because running the actual um, application itself takes about 20 to 30 minutes. So I'm going to cut to the point where I get the output. Rhythm has completed its classification task for this data set. As you can see, the stacked model accuracy achieved 85%. We have 79 northern cardinals correctly identified, 10 misclassified, and same for the black-capped chickadees, 74 correctly identified, 17 incorrect. So this is an overview of the different scores. I guess you could sum it up in a classification report if you want. So the overall accuracy, I'll go ahead and talk about the F1 score for overall both classes resulted in. We have the 85% accuracy for both classes. That this basically means that there does seem to be some, these numbers might look nice, but the fact that they are so consistent, is a good and kind of a uneasy sign that this algorithm might be performing really well, or it might be performing a little bit too well and maybe overfitting in some areas. So this shall be explored further later on once I am able to kind of conduct a little bit more research on what exactly to perform there. So these are the individual precisions. It seems like Northern Cardinal is more correctly identified out of the two, but the overall model has a better memory recall of the black-capped chickadee audio samples. So that's also an interesting fact. I don't have an immediate reason for that difference, but it probably definitely has some meaning in the overall classification process itself. And of course, these results are going to vary over different sizes of data sets. So given the fact that, like I said, the overall classification task correctly identified the samples from the confusion matrix output itself and the performance results from that pretty much tell us that this model is performing nicely, but the only way to really try and true test it is to scale up the amount of data. And from that point, continue to run iterative testing as I have done to get to this point for 85% accuracy on a 900 sample data set of labeled Northern Cardinal and black-capped chickadee audio samples. More of those details are in the report. So another additional feature I added was an output plot, a 2D representation of the principal component analysis of the features. So most of the examples that I was kind of following for building my model, Stephen Call and his research team um, using the deep learning model for avian acoustic recognition classification task. They, of course, used a wide array of different principal components, um, of course, because they have a larger infrastructure. But given my personal research, I decided to, start how I started this project initially, um, with low amounts of data and then scaling up. So starting with two principal components here, um, and principal components, of course, are the um, individual features vectorized together, and that's your main principal component vector. And from that main vector, you can branch off into sub-vectors, um, principal component 1 to principal component n. So there's an abstract amount of principal components that you can have within a system. But of course, the more principal components you have, the more computational space and resources overall that you use up for the overall project. So, given my limited amount of resources, um, of course, I'm going with two for right now, which gives plenty distribution of kind of um, for the two classes that we're identifying. So two principal component vectors actually did quite well for two classes. So as we can see from the output of the data, we have a dense cluster right at the origin. And that is overall saying that there were a lot of similar expressions um, being observed by the overall classification model. And these features can include the male frequency substral coefficients, the chroma features, as well as the zero crossover points. So it's quite a number of features that's included in the overall principal component vectors, but let's kind of zoom in on the clusters, the outliers. As you can see, these are probably bad samples that could not be classified one or the other, and are thus kind of your general outlier. Just since there's not a massive amount of outliers, it is safe to say that even given this cluster right here, majority of the data is going to be around the cluster region. And as we move along the x-axis, we are generalizing more attractively towards the principal component 1. And any position along this 2D PCA plane is basically there in its resting position because of the weight that is contained within the principal component vector. So the weights themselves are calculated based off of the initial features themselves, but the entire point of principal component analysis is dimensionality reduction. So this improves the model not only in the classification aspect, but the overall computational aspect, as well as the the combination of the two and how they contribute to the overall classification task. So with all that being said, let's zoom in on our main cluster. And as we get closer and closer to the data, this is a pretty good point right here. We're gonna focus right here on the origin, right here. And we can kind of see the distributions of the classes. It's really interesting. This is a general plot, so a better plot for the future would include exactly which features these correspond to. But the good part about it is it does show where on the classification spectrum a particular class is identified. So let's zoom out a little bit. Okay. So kind of focusing in right here. This is a pretty good distribution. Definitely not perfect. You know, for 85%, you can see we don't have a clear boundary between the classes, but it's visually obvious, kind of thinking from the perspective of the model itself, how it went about classifying the audio samples themselves and where exactly they landed on the spectrum. And given these two birds themselves do have similar tones, this is actually a pretty good use case to kind of start out with testing, because it's not as simple as an A or B classification. It's still A or B classification, but in a way where your two classes are so similar that the overall classification task itself becomes a hurdle that you have to adjust for. So the only way to adjust your classification is to tune your model based off of data like this and iteratively increasing these tunes until you reach a desired accuracy. And, you know, currently with where I'm at, 85%, it's taken quite a bit of research itself to get to this point to kind of understand how the actual audio classification task itself is performed versus image classification. Um, Not taken away from the complexity of image classification, but compared to audio files, um, they seem to be a little bit more dynamic, especially in the spectral audio frequencies, and extracting good features from there, because the model doesn't have ears to listen, so it's basing its classification solely off of these features extracted from the actual frequency itself. So from that, you're you're deducing a complex entity such as a frequency from audio signal to a numerical value. So with this being said, seems to be an interesting outcome, and it shows that improvement in the model is totally something that could be achieved. Since 85% could be achieved, these boundaries between the two classes can improve as well. So overall, this is the 2D principal component analysis of the features using just two principal component vectors. This is an output plot of my confusion matrix and exactly kind of where each data point was classified. I pretty much went over what it kind of represented from my terminal output, so I won't spend too long on this. This is just kind of a color-coded version of the overall output. So this is the distribution of the first feature plot. Each of these histogram bars represent various bins for the various features that we're using, and basically the frequency of those features in the overall aggregate and how they're dominating the overall feature space is definitely a good output to achieve. You need to know this stuff. Given there is a pretty good convergence along the actual distribution itself, shows that it's not perfect, but it's not terrible, and it's definitely promising if you can scale up the amount of audio samples that I'm using in the overall model. And this gives an overall kind of perspective of what features are contributing the most for this task and how many of them are there. So, like I said, this is good for kind of determining if there's any biases within the data, as well as if particular features kind of need to be not even worried about. And I don't have the particular features each bin contributes or corresponds to. So in my future demonstration, I shall put that corresponding label on the plot. So thank you, and I hope you enjoyed.